So we've talked a lot about, radiation. So specifically concentrating on the biological effects and what we use radiation for, both biological and non-biological. So just a real quick review, ionizing radiation. So ionizing radiation is any kind of radiation like alpha, beta, gamma, X-rays, things like any kind of electromagnetic radiation, and alpha, beta, gamma. So gamma is electromagnetic. That can knock electrons off a molecule or break bonds or create free radicals. And I'm going to show you what I mean by what a free radical is. So what happens is the energy gets transferred to the damaged cells, and then it causes the cells to malfunction. And this can happen in a couple different ways, and we'll look at that in just a second. So just so you know what is ionizing and what is non-ionizing, I put a nice little cool little thing here. So here's your microwave ovens. This is your electromagnetic radiation. And here you have, so high UV rays can be ionizing. So there's different types of UV rays. There's UVA, B, and C. B and C can be ionizing radiation. That's why UV light, i.e. the sun, can give you skin cancer, right? Because it can damage your cells and it creates free radicals, which then can damage the DNA, which makes the DNA go kind of haywire and start reproducing these damaged cells, and that's cancer. And so UVA, so there's UVA, UVB, UVC. UVC, we don't have to worry about. The ozone layer blocks that for us. UVB, that's why we wear sunscreen. It's because of our UV or UVB rays. UVA rays, those are the ones that cause wrinkles in your skin. Okay, now the other ionizing radiation is X-rays, and then you have gamma rays. Okay, so now there's two different types of radiation that can occur. So we have the direct and indirect. So ionizing radiation can either directly damage the DNA, which causes these free radicals, which we're going to look at, or it can indirectly damage the DNA. Now, how it indirectly damages the DNA, it actually comes from mostly because of water. And so what happens is the radiation hits the water and it creates what's called a free radical. So you see this right here? That little line there, that's a free radical. So you remember when we had Chem 219 and 209 and we did Lewis structures, right? And we had right? And everything, here's water, right? And it came, the electrons came in pairs. A free radical is that. It's an unpaired electron. These are very reactive, very unhappy molecules, right? So free radicals will react with anything. And this free radical can then go ahead and damage the DNA. So it can happen directly or it can happen indirectly. But basically what the radiation does is it affects the DNA, and then the DNA all of a sudden starts reproducing in an abnormal way, causing cancer cells and other cells. We're going to talk about other, not just cancer, we're going to talk about other effects of radiation too. So there's acute effects and chronic effects. So acute means right away. Chronic means over a long period of time. So for example, if a nuclear blast or exposure to a reactor core, that would be acute. And this can cause a weakened immune system, lower the ability to absorb food, and death. But the death is usually from infection, and we're actually going to look at all the different ways of acute irradiation today. Now, chronic effects are going to be more common. These are lower doses of radiation over a longer period of time, and this is usually what's causing the DNA that doesn't get repaired properly. It also can damage reproductive organisms or reproductive organs, and cause genetic defects in offspring. So we have acute and chronic. So we're going to kind of look at those for a little while. But first, let's look at how we measure radiation. Now, I'm going to tell you this. You're not going to have to do any calculations with this. You're not going to have to know the difference of these. I'm just telling you, this is just like for your information, and we're going to go over all of these in the next couple minutes, okay? Okay, so we have the Curie. Guess who that was named after, right? And so we have the Curie. We're going to go over all these. We have the Gray. We have the Rad, and REMS, and RBE. It's like, wow, oh, yeah, there's a lot. And don't forget about the Becquerel. That was the original measurement. Okay, so this is how we measure it. So the Curie is kind of just it measures the activity of the source. So if we want to measure the decay, right, we might measure that in a Becquerel or a Curie, like when we talked about our radioactive decay, right? But now if we want to talk more about the biological effects, then we're going to be talking about Grays, Sieverts, Rads, REMS, right? So a Gray, and it's abbreviated GY, measures the amount of energy absorbed by body tissue from radiation. And so that's our Gray. And here's the conversions. But again, you're not going to have to do any calculations with these conversions. I'm showing you how all these were derived, and then we're going to use them to talk about damage from chronic and acute effects. Okay, then you have the Rad, and the Rad, it's radiation absorbed dose. Radiation absorbed dose, RAD. It measures the amount of absorbed by radiation. So you can see these are kind of the same thing, right? They're depending on, it's kind of like when we did like joules and calories. That's where Grays and Rads, they're very similar to each other. They measure the absorbed dose of the radiation. Now the next one talks about the biologically effective dose. Okay, and so this, what it does is, so you'll see these usually REMS. You see, I'll talk about a REM again. Here's your REMS, right? Your REMS or also Sieverts. I know it's a lot of names. So again, this is looking at the tissue damage, and this includes the energy of the radiation dose in Rads or Grays, along with the biological factor referred to as the RBE. And so this RBE is the relative biological effectiveness. And so that's the approximate measure of the relative by the radiation. And so how they figure out the dose in REMS is the Rads, right? And so remember, the Rads is the absorbed dose times the RBE. And so depending on the radiation source, this is different. So like for an alpha, this is times, you multiply the absorbed dose by 10. For a beta or a gamma, I can never make a gamma. Kind of a gamma, right? A beta gamma, it's 1 for both of those. Because remember, that's not a 1. Remember we talked about like alpha is like a semi-truck, so if that actually gets into your system, it's incredibly different because its ionizing potential is so great because it's so big and can make so much damage. But remember, you can stop it with a piece of paper. So as long as the alpha doesn't get into your system, it's not damaging. But if it does get into your system, you can see 10 times whatever the exposure was because of the alpha. Okay, so I have a table here that I think kind of helps explain it a little bit better. So here's the activity of the source. So again, this is like the decays or emission. So like the alpha decay, like how many times it decays like per second or per cycle. And then you have the absorbed dose, and this is Grays or Rads, again, radiation absorbed dose. And this is the energy absorbed from the tissue. And then you have the biologically effective dose, and this takes into account the RBEs, and the RBEs is the alpha, beta, or gamma, right? And so remember our RBEs, right? That's the relative biological effectiveness, meaning how much it affects alpha, beta, gamma. And again, these are like saying, you remember when we did like torrs and atmospheres, and right when we did pressure, we had all those units for pressure, just different units, right? So we kind of have 3 things. We have the activity of the source, the amount absorbed, and then the biologically effective dose, how damaging is it to the system? So we're going to be using these terms really we're going to spend our time when you see these tables when we talk about our discussions, we're really going to concentrate on REMS because again, REM takes the absorbed dose and the source, alpha, beta, gamma, x-rays, etc., into account. So this is really kind of like, this is the one we're going to be using. Okay, so how do we determine the biological effectiveness? How do we determine these REMs? So remember, the more radiation, the larger the effect can be. The more energy that radiation has, the better it is at ionizing, the deeper the effect, right? Like we talked about how, you know, alpha can be stopped by a sheet of paper, beta can be stopped by lead, gamma might be feet of concrete. So all of these things go into the biological effectiveness. And then the more ionizing it is. So when we talk about who can ionize better, remember alpha is the best ionizer, right? But it's the worst penetrator. So let me just review these two just really quick, the difference between penetration and ionization, just really quick. So remember the very first time I talked about how alpha radiation is like a semi-truck going through traffic, right? So it's very, very, very bad at penetrating, right? Paper stops it. But if it gets through, it makes a ton of damage, right? But our skin can stop it. So as long as we don't directly have alpha in our bodies, we're good. Very poor at penetrating. Now, beta is like a four-door sedan through traffic, right? Like a Camry or a Corolla or something of that sort. So it can move through traffic a little bit better. It's also better at ionizing, right? Now, gamma is like a motorcycle through traffic. It's like shoo, 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 right? Gammas go right through our bodies. But because of this, the amount of energy, it's the least ionizing of them all. But we're going to see that gamma is the one that we use most often, beta a little bit. We never really use alpha in biological anything because, again, it's like introducing a semi-truck to your system. You don't want to do that. So when we're talking about biological, we're usually talking about betas and gammas more often than betas. And it also depends on the radioactivity or the half-life of the nuclide. So if you've got something that has a half-life of 1,000,000 years, it's not as dangerous as maybe something that has a half-life of 6 hours. And the biological half-life of the element and the physical state of the radioactive material. So we're going to look at all of these to determine the biological effects of radiation. Okay, so quickly, I know this is a lot. So here's all the different types of radiation that we can, not all of them, here's a lot of these that we can run into, and we're going to talk about these. And you're going to see, these are all in millirems. See, millirems, right? And so we talked about how we get these millirems, right? And so, for example, we look at this, here's our natural radiation, here's medical procedures, and here's consumer products. So natural radiation, radon gas, right? This is the one that we talked about that causes, it's the second leading cause of lung cancer, and the leading cause in lung cancer for people who don't smoke is radon gas. Look at the exposure on here. A plane ride, a little bit from our plane ride, a whole body dose. I don't have in here, but like, do I have this? Terrestrial radiation, natural radionucleotides in the body. Yeah, eating a banana, by the way. That one's going to give you just a little bit, just a few rems eating a banana because of the potassium in there. There's radioactive isotopes of potassium. Okay, now if we look at medical procedures, here's x-rays. You can see about a little bit more than a plane ride. Dental x-rays are a little bit more. Let's see here. Here are the ones we're going to talk about, kind of like these. This is when they actually inject tracers into the body. And so you can see there's a pretty big difference here when they start injecting actual radionuclides into a body versus just the background. This is more of the x-rays. Mammograms are sort of in the middle, but they're still x-rays. And then consumer products. Look at this one. Who knew that smoking had so much radiation in it? But it does, right? So tobacco products, 30 cigarettes a day, 16,000 milligrams. Look at the magnitude of this one compared to everything else, right? More reasons not to smoke. All right. So what are the biological effects? So quickly, these are all millirems. See, these are all millirems. I'm going to change the scale here to rems because millirems are not nearly as dangerous as rems. So you can see that would be 16 millirems, right? This is the only one that really could even, 16 millirems would be smoking. And so you can see biological effects of radiation here. And again, this is the amount that's dangerous to humans. So 20 to 100 can cause decreased white blood cell counts, increased cancer risk, hence why smoking is like right there. 100, 400 radiation sickness, cancer risk, and then 500 plus death. So again, here's just another cool kind of way to look at this. It's just something we don't really see or in our normal life, but it's all around us. So I kind of like this graph here. So again, these are millirems. This is kind of just a different way to see how, it's the same thing I just talked about. See, here's like 2.5. But just so you can see the different on a graph instead of just a table. So here's our annual background dose, about 620, just by hanging out, living, not doing anything particularly dangerous, eating bananas, walking around. That's our typical dose. If you got a whole body CT scan, you can see double your dose for the year. Okay. Now, let's talk about this. Hold on. So let's talk about these, actually using these radio tracers, not this one, actually using these radio tracers in the body. So we're going to use these radioisotopes in the body. So you might have actually had, if you've ever had, it would be called like an MRI with contrast, or you had to drink some, like a beverage, like before you had an MRI or something of that sort, you've probably had a radioisotope. So they use these radio tracers, and so certain organs absorb most or all of specific elements. So specific radionuclides like certain organs, and I'll talk to you about those. And so you can measure the amount absorbed using these tagged isotopes, and you can use a Geiger counter. And the Geiger counter actually measures the gamma or the beta rays given off by the radionuclide as it decays. So as it goes through decay, it actually measures the decay coming out of your body. Obviously, you're going to want to use something with a short half-life, or you're going to have to sit there for hours on end, right? So you want something with a short half-life so you can measure it in a reasonable amount of time. And again, you don't want something that's too dangerous, like an alpha. You would never use an alpha decay because that would be very dangerous to the body because it's so ionizing. So it's usually betas or gammas. And so there's like 100 million nuclear tests performed everywhere in the performed every year in the United States. So, okay, so there's 4 main tracers. So this is what I mean here by certain organisms, like certain tracers. So like, for example, technetium really likes, what is technetium like? I can't remember. I know thallium really likes hearts. Iodine, it really likes thyroids, liver, and the brain. And technetium likes heart, liver, and lungs, right? Heart, liver, and lungs likes technetium. And then sodium, they use that one to measure blood flow because they inject like radioactive sodium chloride salt and watch it go, and they can see blood flow using sodium-24. So there's all of these. So it's technetium 99, iodine 131, sodium 24, and I don't know, what's thallium? TH? Or is it TL? I'm not sure. I don't remember. But I know it's 201. Those are the four main ones used. And this one's really interesting, has another interesting thing, not used as a radio tracer, but in Chernobyl, if you remember, Chernobyl was a nuclear meltdown where the core literally melted down due to operator error. One of the pieces of uranium decay is iodine-131, and iodine loves thyroids. And so one of the biggest issues after the Chernobyl meltdown was thyroid cancer, because this iodine-131, which was released when the reactor melted down, it immediately absorbs into the thyroid. So what they do in the United States, and I'm sure many other places, is an iodine-31 has a really short half-life, which means it's gone very fast, right? And causes lots of damage very quickly. And so what they do now in nuclear reactors, and anybody who lives within a mile of any nuclear reactor, they actually give them iodine pills. And so if there is some kind of a nuclear accident, anybody in that area takes their iodine pills, the iodine pills, again, go straight to the thyroid. The thyroid gets filled with good iodine. And so then when in the nuclear accident, when the iodine-131 is released, there's nothing more to be absorbed because the thyroid is already filled with iodine. And so it's an actual way to prevent thyroid cancer by taking iodine pills. So I always tell people, because, we live sort of by San Onofre, but the chances of a nuclear meltdown are very, very, very small. Seaweed, very high in iodine. So if you can't find iodine pills, have some sushi. Very high in iodine sushi. Okay, so that's a little side note about iodine-31. But again, certain elements just gravitate towards certain organisms, towards certain organs. I can talk today, which helps us use them in nuclear medicine. So here examples are more of them that are used. Now, again, these have very short half-lives, right? So you can't just have them prepared. Right? So they're prepared on site in labs, in the hospital. So nuclear medicine, that's kind of a cool, if anybody ever thinks about that, people don't necessarily think about it, but in hospitals, there's people who actually prepare those things in the hospital themselves because they are unstable. You can't really send, you can't really send any technetium because in 6 hours it's gone, completely gone from the body. And again, here are the organs. They just tend to absorb, like this iodine really loves thyroids, right? Phosphorus loves the eyes and liver. Strontium, big fan of bones. So depending on what a doctor is looking for, they're going to use a different tracer, right? And so if you've ever had like a stress fracture or something of that sort, and they're like, okay, you're going to sit here for 3 hours and we're going to watch this, they gave you strontium, right? So if you've ever had any athletes, that's the one you had strontium. Okay. So now some non-medical uses of radioisotopes. So just really quickly, what else can you use nuclear chemistry for? Well, you can use it for art because older pigments had radioisotopes in them. So you can use it to date art. They use it in crime scene investigations, kind of cool. They can use it to measure the thickness of industrial materials. They can track the flow of different isotopes. They can figure out temperatures, weld defects, road thickness, radioisotopes, very useful. They're using in agriculture to work they use it in trace fertilizer use, developing disease-resistant crops. They'll use it to irradiate food to kill anything that they don't want on there. Treat computer disks, all sorts of things nuclear chemistry is used for. Non-stick pan coatings. Now, it's not in the non-stick pan coating. They use it to form the pan coating. There's no radioisotopes in your Teflon pans. Photocopiers. That's right, you're not supposed to touch I don't know if you know this, but photocopy, you're not supposed to touch like the toner. And they also use it to sterilize things, like I talked about, cosmetics, hair products, other personal hygiene. And again, they use it for food too. They irradiate food. All different things you can use radioisotopes for. Okay, so that is everything radioactivity we talked about. So we talked about really the chemistry of it. Now we talked about the biological uses and non-biological uses of it. But that's all we have for our nuclear chemistry.